Our last section in the statistics lessons is linear regression, which you've probably heard before as line of best fit. The last bit of data analysis we're going to look at involves evaluating the relationship between two variables. For example, we could compare the heights and weights of a sample of teenage boys. Just as before, let's start by visualizing data. The scatter plot is a graphical display that is most commonly used to show two variables and how they might relate to one another. It's a graph on the coordinate plane that contains 1 point for each pair of data values. So it's just a bunch of points. When data are plotted on a scatter plot and there appears to be an upward trend, then we say it's a positive correlation, upward from left to right, that is. If left to right it appears to go down, there's a negative correlation. And if it doesn't appear to do anything, then there's no correlation. Consider the relationship between the following variables and what kind of correlation might show up in a scatter plot of the data. The side of the variables would likely have a positive correlation, negative correlation, or no linear correlation. The number of cigarettes smoked and the possibility of lung cancer. Well, I think data tells us that you're more likely to get lung cancer if you smoke cigarettes. So that would be a positive correlation. The number of minutes spent on social media sites by college students and their first semester grades. What do you think? If you spend all your time on social media instead of studying, your grades will probably be going down. So this would be a negative correlation. The amount of credit card debt incurred by college freshmen and their IQ score. Well, I don't think the amount of debt you incur is directly related to your IQ score. Maybe it is, but I don't think so. So we're going to go with no correlation. The Pearson correlation coefficient, rounded to the nearest thousandth, is a value between -1 and 1 that measures the strength of a linear correlation. For a sample, it's represented by the variable R. If there's a very strong positive correlation, R will be close to 1. If there's a strong negative correlation, it'll be close to -1. The closer R is to 0, the less correlation there is between the variables. So we want to be close to 1 or -1. Example 2, I'm going to come back to it because we're going to be doing that on Excel. You can also do it in your calculator, your graphing calculator, if you remember how to do that and you have one. But again, we all have Excel, so we're going to focus on how to work the problem there. In the meantime, let's go ahead and look at example 3. The level of confidence is the probability that the assertions, it would be assertions, but anyway, made about the data are correct. The level of significance is the probability that the assertions made about the data are incorrect. And if we take the level of confidence and add the levels of significance, we should get 1. So this is a table of the critical values of the Pearson correlation coefficient. So depending on what n is, and that's your number of data values, we've just got 4 to 12 here. Here is listed your correlation coefficient for either a 5% or 95% level of confidence or a 99% level of confidence. And I say 95 would be here, and that's why the coefficient is 1 minus 95.05, and 99% is here, where the coefficient is 0.01. If the absolute value of R is greater than the critical value listed in the table, then R is considered to be statistically significant, which means it's unlikely to have occurred by chance. It's important conclusions. Use the critical values to determine if the correlation between BMI and age, in the example 2, which we'll look at more in a minute, is statistically significant. And we found in example 2 that R is 0.5763078191, and we're going to use a 95% or 0.05 level of significance. Okay, so when we pull up the Excel sheet, you'll see that N is 12. We need to know that. And it says use a level of significance that is 0.05. So we look back at the table for where 12 and 0.05 are. It's 0.576. So the critical value is 0.576. The absolute value of R is just 0.5763078191. And we want to see, is that greater or less than 0.576, our critical value? 0.576, but then we have more, right? So the absolute value of R is greater than the critical value, which means that our situation is statistically significant. Not by much, but it is. So we can say that we have enough evidence to conclude that a linear relationship exists between BMI and age for male ultra marathoners. That's what example 2 was about. Okay? So let's go back and read example 2, and then we'll get on the computer. The following is a small sample of data collected from male participants in a 161-kilometer trail ultramarathon. The survey collected the BMI, body mass index, of each participant and their age. A table of the data, along with a scatter plot, is given. Use Excel to find the correlation coefficient R between the variables. And so here's our data, and you'll also find this on Excel. So let's go over there. Pull up 8.5 examples 3 and 4, and we'll look at these together. Actually, this is example 2, not 3, but okay. Okay, so we've already read our problem about the sample of data in that's BMI mass compared to age of these marathon runners. And the first thing we want to do is create a scatter plot. Now, I'm going to make sure that on your notes you have, yes, on your notes you have this, the list of how to do this, okay? So you can print that out and look back at it whenever you need to. So to create a scatter plot, first select the data. Then you go to Insert. Then we're going to look for the little thing that looks like a scatter plot right here. And then we select the one that looks like a scatter plot right there. And there we go. We have our scatter plot. Okay. If we want to add a trend line, and we do because we need to add a trend line before we can find the R value, then you go to where it says Chart Design. We're already there. And you can go there by just clicking on the graph itself, okay? And it'll take you to Chart Design. Then add a chart element down to Trend Line, and we want a linear trend line. So it puts a line on there, but it doesn't tell us anything. Doesn't tell us what the line is, doesn't tell us what R is, nothing. So we gotta go find that. So go to where you are on the line and double click. And then some information pops up over here. So we want to set it to display the equation on the chart. We're not going to say to display R squared because we just want R. So we're not going to worry about that. Just display the equation. And we can hit X, and there's the equation. Very tiny. Can I not make this bigger? Well, doesn't want me to. Okay, anyway. So there's the equation of the line there. 4.4732x minus 60.085. And we can see that the data is positive, has a positive correlation. Now we want to find R. So here's how we do this. We type equals Pearson, parenthesis. Then we want the first set of data and the second set of data, or the X values and then the Y values. So we're going to select all these values, comma, select these values, close, enter. There's R, okay? 0.576308, just like we talked about in example 3. So there's the R value for example 2. That's how you find it. Now, before we finished with example 4, in example 4, it says a recent study sought to find if any correlation existed between childhood weight and self-esteem. Children between the ages of 9 and 11 were surveyed. Weight was measured in pounds, while self-esteem was measured based on the average of the answers to 15 questions that they asked the participants to rate themselves on a scale of 1 to 5, where higher scores meant higher self-esteem. So here's the data for 12 cases. And we want to start by finding the R value, because the first question asks us, is R statistically significant at the 0.05 level? So we need to find the R value. So I'm going to do that pretty quickly. And we can do it. We don't even have to find the scatter plot and all like we did in example 2. We can just type equals Pearson, parenthesis, and then select the first, select the second column, close. Make sure you're not selecting the words in there, just the data. And so there is our R value for example 4, negative 0.605065. And so we'll pick up right here back in our PowerPoint. Okay, so here is example 4, and we found the R value, and the absolute value of the R value would be the absolute value of negative 0.6051. So that was positive 0.0651. And we wanted to find out if it was statistically significant at the 0.05 level. So we look back at our table again. N is 12 again. And at the 0.05, we have 0.576. So 0.6051 is greater than 0.576. So we can say that this information is statistically significant. In part B, we were supposed to find the line of best fit again, the linear regression line, but you do it just like we did in example 3, okay? And you find that it is negative 0.084x plus 8.722, okay? So if you have a graphing calculator or you remember how to do it on there, go right ahead. If not, look at example 3 that we just did in Excel and go through the steps there. Oh, back on part A, it also asked us, how about at the 0.01 level? So how would that compare to the 0.01 level? So if we go back to that table, if N is 12, 0.01 is 0.708. So in this case, at the 0.01 level, we would not be statistically significant. So it just depends on how close you want to be. If you're only looking at the 0.05 level, then we're good to go. If you're trying to get a closer estimate, it's not going to work. C says, if appropriate, predict the value for the level of self-esteem given that the child weighs 64.1 pounds. Okay, so a child of 61.4 pounds is within the range of our data set. So we're just going to plug in 61.4 for x in our equation. Or 64.1, excuse me. We get 3.3, so their self-esteem would score a 3.3. D says, if appropriate, predict the value for the level of self-esteem given that the child weighs 45 pounds. This is not appropriate. Why? Because in this case, 45 pounds is outside the range. It's less than all the other data values that we looked at. So it wouldn't be correct to assume that the information that we found would apply to someone with a weight that small. Okay? I think I wrote that wrong. There we go. Okay. One more. If appropriate, predict the value for the level of self-esteem that the given that the 13-year-old weighs 88 pounds. Well, if you'll remember, these values were only children of ages 9 to 11. So a 13-year-old would not be in this data set. It wouldn't be appropriate. Okay, so that concludes our section. One more section of statistics, 8.5, or section 5. We're looking at line of best fit. It says, the table shows the hours studied and corresponding test grade earned by students on a recent test. Calculate the correlation coefficient, R, and determine whether R is statistically significant at the 0.1 level of significance. So the easiest way to work these, you could do it in Excel, which you will have to do for one of your labs, but I provide an example along with that lab for how to work these in Excel. So I'm going to work these in Desmos. It's a little bit easier, and I'll add that on here in a second. But what you do is you'll enter your table into Desmos, and then once you do that, you type Y1 and this little squiggle, B plus MX1. Or MX plus B. I'm doing it B first because of the next example. And it tells us that the R value, we don't need to know the line of best fit in this one. We just want the R value. And the R value is 0.752. We want to compare that to, or the absolute value of R, which would be positive 0.752, and we want to compare that to our correlation coefficient, or to our level of significance at 0.01. So here that is. So at 0.01, let's see, what is N? There's 12 of these. So N is 12. So 0.01 at 12 is 0.708. And notice how it says here is R is statistically significant if the absolute value of R is greater than the critical value. And yes, in this case, it is greater than. So yes, we are statistically significant. And then for example 2, this table gives data for the average temperature and snow accumulation in several small towns for a single month. Determine the equation of the regression line. And notice how it puts b naught plus b sub 1x. That's the same thing as mx plus b, but there's a little catch. When you put in your answer, you have to have the b naught first. So it has to be in this order here, or it's not going to count it right. Just a fair warning. Then determine if the regression equation is appropriate for making predictions at the 0.01 level of significance. So again, we're going to enter it into Desmos, and we'll put in y1 squiggle b plus mx1. Okay? And it comes out that our equation in that form with b coming first is 32.268 minus m was 0.568 and then times x. And it tells us that r is negative 0.7108. So we compare the absolute value of r, which would be positive 7108. And in this case, n is 10, I believe. We're just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. And we want the 0.01. So back over here, 10.01 is 0.765. And we want the absolute value of r to be greater than that, and it's not. It's less than. So that means that our equation is not appropriate. It is not statistically significant. The second example over here in Desmos. So what we do is we go to this little plus, and we're going to add a table. And we put in our values. So we have, under the x values, we have 40, 28, 17, 40, I think that's a 37, 20, 32, 17, 28, and 43. And then under the y values, 7, 13, 21, 10, 11, 25, 28, 20, 11, and 5. Okay, so hit enter and it'll take us down to a second area here, and that's where we're going to put y1, and you don't have to worry about putting the sub in somehow. If you just type y and then 1, it'll automatically take it down. And then we have the tilde button, which is in the top right corner of your screen. Or if you can't find it, it is in here somewhere. There it is. And then b plus mx1. And there we go. So it tells us b and m, and that's what I've put over here. And it tells us r, which we compared to the coefficient or to the level of significance, and that told us it was not statistically significant. Okay.